For the first time in history, buildings can exist in two places at once. One is physical, the other is digital. The digital twin is not a static 3D model, it is a living simulation connected to real-time data from the building's water system. Every flow, every pressure change, every temperature variation is mirrored instantly. This transforms invisible infrastructure into a measurable and predictable environment. Traditional building models are created during design and rarely updated. They represent how the system was supposed to work. A digital twin represents how the system is working now. Sensor data continuously updates the model. This allows engineers and facility managers to see real operating conditions, identify deviations, simulate future scenarios. The model becomes an operational tool, not a design archive. In conventional buildings, hydraulic behavior is hidden. In a digital twin, it is visible. You can observe flow, direction, pressure gradients, hot water, circulation, performance zone imbalances. This makes leak detection faster and more precise. Because the system shows not only that something is wrong, but where and why it is happening. Every pipe, valve, and pump has a lifespan. But in most buildings, maintenance is reactive. A digital twin allows predictive analysis. By combining material data, pressure history, temperature cycles, flow patterns, the system identifies components that are approaching failure. Repairs can be scheduled before a leak occurs. This eliminates emergency interventions. In large buildings, a leak detected at the main meter gives no location information, but a digital twin compares real sensor data with the expected hydraulic model. When a deviation occurs, the system calculates the most probable location. This reduces inspection time from days to minutes. Maintenance becomes surgical instead of exploratory. Digital twins are not only about preventing damage, they improve efficiency. By analyzing real demand patterns, the system can adjust pump operation, reduce hot water circulation time, optimize pressure levels. This lowers energy consumption, water waste, operational cost. The building learns how to operate itself more efficiently. One of the most powerful features of a digital twin is simulation. Engineers can test scenarios without risk. What happens if a pipe bursts on the 10th floor? What happens if fire systems activate during peak demand? What happens during a power outage? The system predicts the outcome and identifies vulnerabilities. Resilience becomes a design parameter even in existing buildings. When digital twins are connected to control systems, they move from observation to action. The model does not only detect problems, it corrects them. Pressure is adjusted, zones are isolated, flow is redirected. Infrastructure becomes self-regulating. A building that understands its own water network can protect itself. The future of water management is not only in pipes, it is in their digital reflection.